Hello, everyone. Thank you for coming to the INDUS talk. It's been going really well since last few months, just because of you people who come and attend these talks from different places in the world and during different time zones. So thank you, everyone, for coming. And we have Nitin Vashishtha today as our speaker, who is a PhD student at ARIES, Nainital in India, and he'll be talking about the effect of polar magnetic field and helicity injection in a breakout CME today. So if you have any questions about the talk, you can just stop him wherever you want and ask him your questions. So thank you so much. So Nitin, over to you. I think you can start your talk.
Thank you, Yami, and thank you for giving me this opportunity to talk about my work on this platform. So I'll be talking about the poloidal magnetic field strength effects on a breakout CME and also the helicity injection in a breakout CME scenario. So first I'll introduce what for the sake of completeness, what is the CME. So so
Yeah.
I think you lost me. I think, is it right?
Yes.
Yeah,
Yes.
so I'll start again. So I'll be talking
Sure.
about the
Okay.
effect of poloidal field strength on a breakout CME scenario, and also the helicity injection into the breakout CME system. So first, I'll introduce what is a CME and how does it look like. So when we talk about the CMEs, so this is a last cosine image when we see through a coronagraph. This is how a typical CME looks like, and these, so as per the definition, these are the bubbles that propagate outward in the solar atmosphere, and they contains plasma, and they also contains the magnetic field. So a typical definition is like any observation change in coronal structure with the time scale, few minutes to few hours, associated with the discrete bright white light feature is classified as CME. So they are typical as they contains the plasma and also the magnetic field. So they affect our space weather as well, and they can cause the geomagnetic storm as well. And their typical speeds range varies from let's say 100 kilometer per second to greater than 2000 kilometer per second. And this is the speed I'm talking about, the plane of sky speed here. And their width is also the plane of sky width can range from few degrees to 360, where the few degrees of the width is as classified them we classify them as some people say this they are narrow CME, and for the 360 degrees one, we call them as CME, as they appear when the CME is propagating towards you, towards the instrument, towards the chronograph. So it appears like it's a circle around the occulter, and then we say the width is 360 degrees. And the mass is 10 to the power 12 to 10 to the power 15 grams. So these are the observational features that we see that when we observe CME, how their kinematic parameters, like what are their speeds, what are their acceleration, what their mass is. Now the another question is that how do they originate? So what are their initiation mechanisms? So there are primarily two school of thoughts, and one says that there is a pre-existence of magnetic flux flow in the solar atmosphere, and when it gets destabilized due to the stratospheric motions as well as some instability, so they erupt into the solar atmosphere. And these are the some of the pioneer works by Forbes and Eisenberg, where you see that there is a existing flux flow, and due to some instability, it moves upward in the solar atmosphere. And also the some of the work, the initial work by Gibson and Lowe. This is also one of the model in which we have the existing flux rock in the solar atmosphere, and it into the heliosphere. The another thought that says that the formation of the flux rock due to the shear magnetic arcade. So what happens that there is the flux rock that formed due to the shear motion of the magnetic arcade system in the solar atmosphere. So there is no existing prior existing flux rock, but this flux rock forms after the connection by the shear magnetic shear at the base of this magnetic arcade system. And some of the work by Mikech, here we can see there is a dipole magnetic field, and when it is stretched, so the flux rope also the flux rope forms after the reconnection, and it erupts into the heliosphere. Then this is the for the dipole magnetic field strength, and one of the model by Antiochos says that they in the multipolar scenario, when we apply the shear at the base, it result in the formation of the flux rope and which erupts into the heliosphere. So primarily these two are the models on which people generally do the MSD simulations to understand the CMEs in their behavior in a better way because of the constraint on the observation. So in my work, I have used last model, which is by Antiochos, which is in a multipolar scenario where where we form the flux rope by applying the shearing at the base, and which result in a CME. So and which is also called breakout CME. And here and for in this work, I mainly see the effect of the poloidal field strength in this breakout scenario. And for the motivation is that in the last cycle, we saw the cycle 24 is relatively a weak cycle. And so we want to study the what is the how does this global background magnetic field affect CME eruption. So for that we change in our simulation. I'll be talking about it in detail. So we play around with the background magnetic field strength, and we see how it affects our CME eruption. And the another thing that that the importance apart from the CME, apart from the studying the various parameters of CMEs, is their prediction. So for the prediction sake, the people has been using sharp parameters to investigate how, but what are the global parameters on which a CME eruption can, we can we can explain that this is the parameter in which the CME eruption is relying. So so these two are the main motivation behind this work. So for that, we, as I discussed, for my simulation in this work, we have used the breakout model in which we have a multipolar scenario, multipolar magnetic field strength, and we applied the shear at the base of one of the arcade system, and which result in a flux rope formation and later into the CME. So we have performed the 2.5D spherical axis symmetric simulations, and this simulation box contains 120 by 120 cell with this design domain, and we have also applied the AMR. This AMR criteria is based on the current density, where we have the formation of current. It enhances the resolution, and so this is yeah. So these are the initial condition for simplicity. We have kept the density because the base of our simulation box start from the base of corona. We haven't included the chromosphere and the transition region because it will be computationally expensive. And we are looking at the larger picture. So that's why we for the starting we have started with the base of the corona, and this is the typical initial condition where we have a quadrupolar magnetic field structure in the background magnetic field, and the background magnetic field is also a dipole in the nature. Has the nature of the background magnetic field is the dipole, and we have in one of the section we have changed this dipole magnetic field strength, this 2.2 Gauss, for different values to see this see its effect on the eruption. And so for this multipolar system we have applied a vector potential. Basically we have applied a vector potential in a given latitude to create a multipolar scenario, and we then we'll let the system to relax, and after the system in equilibrium position it looks like this. And now we can see that the X point uh, came a bit lower because of the gravity stratification. And now after applying the shear, also these are the boundary conditions. So in the we are in the r theta phi coordinate system. Basically it's r theta coordinate system because this is 2.5D. So we have, these are the various boundary conditions we have kept. And so this is the velocity driver. Velocity driver means, as I discussed, that in the case of a multipolar scenario, or in this case we have applied the shear at the base, which result in the flux rock formation. So this velocity driver is a sinusoidal in time, and as well as in the along the latitude. So along the latitude and as well as this time. So this delta t is the typical time that we for which we have applied this velocity driver. In reality, if we compare, it is similar to like how much time is like active region is evolving. So it could be different. So for our work, we have kept 27 hours, but it can be different because every active region can evolve differently. So yeah, so we can tune this parameter as well. See, so now after applying all these result, all these things, we get this simulation, some sort of this. This is the current density map, and in which we see the quadrupolar structure and also see the streamer. And when we apply the shear, so we see a formation of flux rock and also the CME. So and this CME, so this if as I discussed, the time is the 27 hours for this velocity application, and after 27 hours we stop this shear at the base, and this we what we get in the as a final result. Now we change yeah, so for to see the effect of poloidal field strength, now we see we change the background magnetic field strength from 2.2 goes to 2.3, 2.4, and 2.5 goes. And this is how this is the initial configuration. In the right side, I have plotted the B along the latitude at a 1.5 solar radii. So this is how, because this is a low beta plasma regime, and because of low beta plasma, this is the dynamics is highly dependent on the magnetic field. So a slightly change in the magnetic field can result into different scenario. So so we have changed this background magnetic field from 2.2 goes to 2.5 goes, and this is how it looks. Yeah. So when we have 2.2 goes, we get the eruption, and as we increase the field strength to 2.3 goes, we get the failed eruption. The flux rope did form, but it falls back along the magnetic field to the surfaces. And sorry, for 2.4 and 2.5 goes, the flux rope doesn't even form. So we can see that these background magnetic field highly affect highly affect our result, and it also constrain the constrain the CME if we increase it further. So we can say in case of the uh, sorry, so we can say in case of low magnetic field, low background magnetic field, or low magnetic field heliospheric pressure, we can see large number of weaker CMEs as compared we see in the cycle 24. So this is one of the aspects to see we see to check how the effect the different scenario the different CMEs we see in the cycle 24. And for the effect of shear velocity, now this is the other parameter that our result or CME depends on, apart from the background magnetic field, is the shear at the base. So we change the shear velocity at the base to look at which is basically meaning by this how we are changing the helicity in the system, because by applying the shear at the base we are giving the helicity in the system, which so we want to see the effect of this shear velocity at the base. So this is sorry, you can see, yeah. So this is a typical so this is the initial, as I showed earlier, this is the final result we get by applying a certain velocity at the base. I would like to point out that this velocity we are giving at the base is of the order of 30 kilometer per second, which is relatively higher as compared to photospheric velocity. But we, because the domain start from the base of the corona, and at the corona, these speeds have been found from 20 to 50 kilometer per second. So this is somewhat in agreement with the observation as well. So the order of, if we change this velocity slightly within, let's say, 5% of the initial velocity, we get the different scenario. And by so this is the multi-eruption case, where we get, by if we increase the shear velocity of the base further, we get the multiple eruption. So because in the electricity that is injected into the system, it is not carried by the only one CME. Is the this even after the one CME has been ejected, the system still it still has some complexity in the system, that the reconnection happens, and which result in the further plasmoids and further CMEs as well. So for in these different scenarios, we study the different magnetic parameters, which which is similar to the sharp parameters, like the current helicities and also the magnetic energy in these three different scenarios. And one other thing that here is the first eruption is the breakout CME, but the later second eruption is the typical standard flare type of reconnection, where the central arcade has been stretched too much, that it reconnects it with itself. So we also get that also cause a flux of formation. But here we are concerned about the CMEs, so breakout CME. So the first and the last CMEs is by the breakout scenario. And yeah, so this is, here we found it between two breakout CMEs. We also found the flux form due to the standard flare type reconnection. And this is the various magnetic parameters that we studied. So we see that in different scenarios, the magnetic energy increases as we increase the injection, we increase the shear at the base, and after it reaches the maximum value, it decreases, and the flux of form is. For the failed eruption, it declines further, because now this shearing, because it's sinusoidal in time, so it is decreasing. So that's why this magnetic energy also decreases. And for the multiple eruption cases, we see some of the some of the pulses, because in between the two CMEs there are plasmids also forming. So that's why this is the variation we see in the multiple cases. And also for the single eruption case, we see that we see that similarly the magnetic energy increases and then it falls back. So this so main point here is that this magnetic energy and also is not giving us a clear picture. If we, by looking at the magnetic energy plot, we can differentiate whether it is a eruption or multiple eruption or a failed eruption case. So for that we we study the current helicities and the total unsigned current helicity and the absolute net current helicity. So for that, this is the total unsigned current helicity plot, in which we also get see that the current helicity is also for the different cases, we get the it reaches up to similar level, but the rate it is increasing is different for these three different cases. And if we, after the this vertical lines, about vertical lines at the time when the flux rho forms in these three scenarios, so we see that even after the flux rho forms, the helicity, the total unsigned helicity increases. But we can see that for the flux for the failed eruption case, it is after the flux format, it is lying between, somewhere between the multiple and the single. So which is also not giving us a clear picture, the total unsigned current helicity. So for that, the next parameter we studied is the absolute net current helicity. And this plot gives is sort of a very interesting, in the sense that here we see that I have marked this position A, B, and C. And here we see that in the failed eruption and the single and multiple eruption, similar to the total unsigned, the slope of this helicity is different, and it is higher for the multiple eruption case, and it is lower for the single, and much lower than for the failed eruption case. But here the another thing is that this absolute value, the maximum value it is reaching, is almost similar. But for the second CME that happened in the case of multiple eruption case, which is somewhere here, this is the time after 20, this is this dash line. So so before this, the helicity is also increases after D point, and the slope between point D and point E is greater than the failed eruption case. So the result is that apart from the maximum value this absolute net current helicity is reaching, the slope at which it is increasing is also playing a crucial role, whether it will whether the eruption will happen or not. So from this plot, we conclude that apart from the maximum value, this slope at which is this absolute net current helicity is increasing is also, I mean, is also telling you about the eruption. The one thing that I would like to say that these simulations are the ideal energy simulation. So here the resistivity is the role of resistivity is only due to the numerical resistivity. So if we increase the resolution of our simulation, so the velocity at which we are getting the eruption will might change, and we have seen that it changes, but overall the profile of this different scenario remains the same. So so if we do the high resolution simulation, one can see this slope of these plots will increase further, because in lesser time we will get the eruption, we will get the reconnection. But the overall profile we have checked that it remains the same, that the in case of failed eruption, as well as in case of single eruption, and as well as in the case of multiple eruption. So after studying these three global parameters, so we can say that from the observation, one can study the time evolution of these sharp parameters, and especially the absolute net current helicity, because this parameter is somewhat telling us some more, giving us the more insight about the various scenarios of these eruptions. So from the sharp parameter, it is very crucial to study the time evolution of this parameters, because we have seen, sorry, because we have seen that various AIML based studies have been done to predict the solar flare or the CMEs as well. So in that case, the most of the weightage has been given to some of these parameters. So, but it is also crucial to look at their slope as well. So this is one of the major points we get from this study. And so to summarize this work, so we were able to simulate the breakout CME using MPI AMRVAC, and rate of change of current helicity can be a good indicator for the CME prediction along with other sharp parameters. And CME eruption is highly dependent on the polar magnetic field strength. And in case of homologous CMEs, means the multiple CMEs, we get the two CMEs result of breakout reconnection, and one is the standard flare type of reconnection. And in the coming work, currently we are performing the forward modeling of this CME scenario. The constraint of this model of these simulations are that these are 2.5D. So for the forward modeling, we won't be able to do the line of sight integration. But people have done in 2.5D forward modeling, that they assume that some of the depth, let's say 100 kilometer or 50 kilometer, and then they do the line of sight integration. So currently we are performing the forward modeling in the various lines, and we are trying to look at when the CME passes through a particular position, how the line within the various lines is changing. And we are doing this forward modeling the lines that are present in various upcoming instruments like VLC and ViewCom and METIS. And for the next thing, for the next step, what we can do, this is the breakout CME model. What we can do for the flex emergence model for the another school of thought, we can also do study the time evolution of these parameters, and we can see how these are two different in these two different scenarios, because when these two different scenarios where the flux slope is already existing and when it is formed, the evolution can be different, totally can be different in terms of density, temperature, and as well. And in our model, the solar wind, we have only included heating parameters, which include the radiation losses and all the heating, which is dependent on the latitudinal dependence. But if we include the new solar wind model in our simulation, which is more realistic, then we can say furthermore, and also we can also include the lower atmosphere for the next step as well. Yeah, thank you.
Okay. Thank you, Nitin, for the nice talk. I think we have some questions from Satyam and Arkadeep. So Satyam, maybe if you can unmute yourself and ask your questions. I can see your hands raised.
Yes, hi Nitin, thank you for the
I
nice
had
talk.
them.
So I have a few questions.
Yeah, yeah,
And
sure.
the first question is that I think you mentioned that in some of the results where you are seeing the effect of poloidal magnetic field strength.
Yeah, yeah.
So in one of the cases, flux rope doesn't form, or in
Yes,
more than
yes,
one
yes,
case.
yes, yes, yes.
So I was just thinking that since this poloidal field strength is the global strength of the sun, like a
Yes, yes, yes.
global dipole. So
Yeah.
why it should, in physical terms, why it should have any effect on the formation of a flux rope, which occurs in a localized area of the sun, kind of based on the velocity drivers and reconnection mechanism, which occurs locally.
Yeah. So actually, I think in this scenario, what is happening that the reconnection is happening with the overlying magnetic field. The so which is creating a passage for the for the CME. So the pressure from the above overlying magnetic field is higher in case of we increase the magnetic field, and that's why I think that the rise in the central arcade is not able to create the passage. So according to me, I think the scenario is like though this is a global dipole magnetic field in the background, but in the breakout scenario in this scenario, the reconnection is also happening with the overlying magnetic field for the breakout. So I think that's why I think is in somewhere that's how the overlying magnetic field is affecting our system, our eruption. So this is, I think.
So this reconnection with overlying field strength is uh, causing the formation of flux rope or the eruption of the flux rope which has been already formed by
Yeah,
reconnection.
yeah. So I think in see when we increase it for Mr. 2.3, so when in one case the flux rope forms, but it falls back. So I think what it is doing, I think it is because it is also increasing the magnetic pressure from the above, and also it is apart from the this increase in the magnetic pressure, because of that the reconnection is not taking place. I mean, somehow that the reconnection is not taking place with the side with the side neighboring arcade, where central and the neighboring arcade. So I think what is happening, yeah, probably the thing is, I think the increase in the magnetic field pressure from the above is somewhere, I think, constraining the formation of the flux rope.
And the other question that I want to ask is regarding the code,
Yes,
because
yes.
I am not too familiar with the code. So as
Okay.
you said that there is no physical resistivity in the code.
Yes, 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 yes.
So the locations where you want your reconnection to occur, so do
Yeah.
you resolve that location much higher as compared to the location where you want ideal effects to be satisfied in the MPI this code that you are using? I mean, how do
No.
you ensure that reconnection will occur only at the places where steep gradients will be generated?
Yeah, okay. So actually, so that, yeah, you are absolutely right that we are not giving the explicitly resistivity. The only the reconnection is here is mainly controlled by the cell size, basically the numerical resistivity. So in general, so if we are, because we are giving here the shear, because we are giving shear at the certain latitudinal between certain latitude above the equator and below the equator, and that's why we are constraining the reconnection site. I mean, because we are giving the shear only up to only between a certain latitude, not apart from, not everywhere else.
No, if what you are saying is even if you give a velocity shear at a particular latitude, if
Yeah,
it's a perfectly ideal MHD code, no reconnection can occur. It is not
yeah,
possible.
yeah.
You
No,
will have a
yes, yes, yes,
situation of equilibrium.
yes, 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 yes.
So until and unless there is, so you have numerical diffusion which will operate similarly at every
Yes,
pixel.
this is, yes,
So
yes, yes.
until and unless you resolve the reconnection side much higher as compared to the place where you want your ideal effects to be satisfied,
Yes, yes,
numerical
yes.
resistivity will operate across all the entire computational domain in a similar fashion.
Yes, yes.
So that is why I asked how you ensure that the place at where you want your reconnection to occur? How do you, like in implicit large eddy simulation, this is ensured.
Yeah.
Where, so that is why I asked, so do you use a uniform resolution for the entire computational domain, or is it
No, it is
different?
AMR. So as I said, so this is not the uniform resolution. I mean, this is also the stress grid, and also we also have the AMR as well.
Okay, and I have
Yeah.
last question. Sorry for taking so much of time.
No, it's okay.
So,
It's okay.
can you go to the plot of absolute current helicity which you showed
Yes.
versus time, the previous one? The plot just before this slide, I think.
Okay. Okay.
Yes, so in this case, the blue plot, which is corresponds to a failed eruption.
Yes.
So approximately at 15 hours, there is a sudden jump in the profile.
Yes.
Which is not the case for other cases.
Yeah.
So, like, what is the reason for this sudden jump in the profile?
Yeah, so I think this could be because while computing all these parameters, we are assuming that the because we are only computing in the summing in the over whole domain, and we are assuming or sorry, up to the 3.5 solar radii, and we are assuming that because majority of the shear is only in the sum of the localized region, so we are assuming that most of the this contribution in the terms of helicity is coming from there only. And so I think in this in this here when I think after 15 at the 15 hour, the flux flow forms in case of failed eruption, and it falls back in the in this case to the solar atmosphere, solar photosphere. I mean the base at the back to the solar sun. So what happens, I think, so this sudden jump is because that the flux slope doesn't go outside the 3.5 solar radii, where in the some of the other cases, because uh, in some of the other cases that pass the CME forms and it passes through the region where we are calculating. So I think this sudden jump is because of this flux slope is falling back to the region. But I'll look into it, that what is causing in this only in this case, why this sudden jump, and yeah, I'll look into it.
Okay, thank you so much.
No, I think Argadeep, you can ask your questions and then we can take few questions which are in the chat.
Yeah, Nitin, nice talk. So I also had a question about this particular plot that you have. Not this one actually, from the current helicity plot. I think it's the next one. Yeah. So from this, you said that you inferred that it's also the slope of the increase that matters. And that for the failed eruption, you have the least slope, and therefore probably you do not have an eruption. But if you look at the blue line, where you have the blue line, you do have fluctuations. So does it also matter at what level the slope takes the current helicity to? Because localized in time, you may have very high fluctuations, like very steep fluctuations of the current helicity, but that does not lead to an eruption, right? So does the absolute value also matter? Because if it does, then in that case, you have two parameters governing it. One is how much the slope is, and the other is
and how much is
the value that it reaches to.
Yeah, so I think according to us, I think it's both. I think the maximum value it is attaining, and also the slope. These both parameters are somewhere dictating the eruption.
Okay. And did you also look into the change of kinetic energy within the system? Because you are injecting certain kinetic energy, and that will be carried away when the flux slope moves out of the domain, right? So have you looked into the?
Yeah, I think I don't currently have the plot of the kinetic energy, but yeah, we did look into the plot of the kinetic energy evolution of the time, and it is I think it is somewhere. I mean, it is just when the maximum the magnetic energy is increasing, it is also start to decrease somewhere. But I don't currently have the plot. I'll send you.
Okay. Thanks.
Yeah. And so one of the questions from the Ritesh is. So I think first is from Ashwin Namita. For the filament associated CME ejection, are there any parameter like sharp parameter twisted?
I'll read the question for everyone. Hi. I think, yeah. So we have one question from Ashwin. I hope everybody can hear me. That's for the filament associated CME. Are there any parameters like sharp?
Okay, so for the filament associated, I mean, the sharp parameters are generally are the for they are measuring the photos, they are talking about the photospheric level, and they are telling about the active region. So whether what is for the filament associated. So I think whether the CME is, from a particular active region is because of the breakout scenario or the I mean the filament associated like from the flux emergence model. I think this is difficult to say, but because the sharp parameters is only telling you about the properties at the base at the photosphere. So I think okay. I don't think that there is particular there's separate parameters which talk about the filament associated CME if like sharp parameters because sharp parameters are telling about the magnetic field on the photosphere. Or one may
Okay.
comment about this.
Sure. And then we have another question from Ritesh. And could you elaborate more on AMR and the locations where applied for the broader audience?
Yeah, so for the AMR adaptive mesh refinement criteria that we have adopted is like it is based on the current density. So wherever the region where the currents are forming, so it resolve more. Like in the current sheet that is above the streamer, and in the when the current sheet forming in the when the reconnection is happening with the neighboring arcade. So wherever the reconnection is happening and the currents are forming, it enhance the resolution in those particular region.
Mhm. Okay, and then we have another few series of questions by Harshit. I think it's a huge one, so maybe you can also give it a read and I can read it for the audience.
Yeah.
Considering that the rate of overlying fields decreases for some time during and after the reconnection due to torus instabilities and a decay index parameter can give an indication of how fast or slow field decreases with height. My question is, can the results from your model be used to look into relationships with CME true speed from GCS and sort of give an early southwest forecast for CME initiation by looking into model parameters? For example, say this active region CME is giving a particular slope in magnetic helicity, and how the change in the slope can be used to look into the speed of CMEs. And once you have some indication, we might be able to say about the speed of the CME before it initiates. I think Southwest it was a space
Yeah,
weather.
space weather. Yeah. So I think I also have this velocity uh, height velocity time plot. So I think this is for this green one is for the single eruption, and the orange and the blue one are for the multiple eruption case. So if we increase the helicity further, so for the first CME, we see that the this is more accelerated CME, and what happens that after first breakout CME, when the second CME happens, the field lines came to the initial configuration like just before the first CME, but now this helicity is in the system is because has been taken away by the first CME as well. So the second CME that appears to be a slow, I mean the less accelerating CME. And one thing you can say, of course, that with this shear, all these that from all the earlier works are from this work as well, that the CMEs that we are simulating because of the shear, basal shear at the base, most of the all of the CMEs are slow CME. So you can see their speed is reaching, I mean, up to 200. But in the later, if you after the 10 or 20, after 14, 15 solar radii, this saturates around 400 kilometers. So all the CMEs that generated through this model, also this shear based model in the breakout CME, they appear to be a slow CMEs. But yeah, but one can look into the relationship between the helicity and velocity. But one thing is for sure that apart from the helicity, I mean there are many parameters, but one of the parameters is like the overlying magnetic field. Because if we see the flux rope that forms after the first CME, that is fast. That is fast because the overlying magnetic field is still open because of the first CME. So that flux rope speed was almost double of this breakout CME. So yeah, we can say that I mean, we can relate, but how good the relation will be, one has to check for the multiple for many CMEs. And this is only for the breakout. One has to look for the another flex emergence based model as well.
Nitin, I have just one more question.
Yeah.
So in this code that you are using, what is the maximum and the minimum resolution in megameter? So for example, the location at where reconnection is occurring.
Yeah, so
what is
so
the
maximum
resolution of that?
Yeah, maximum it reaches around 7-8 megameter.
And minimum, what is the resolution of the pixel or location where your reconnection actually occurs?
Yeah, so this is the highest. I mean, this is the minimum cell size. This is the minimum cell size that we achieve. This around 7 megameter.
So that if 7 megameter is, that tells me that it is a uniform resolution across the domain.
No, I mean, yeah, it's not. No, it's not uniform. It's like the after applying the AMR, and the highest level we achieve is around 7 megameter. The lowest one where near the 9 or 10 solar radius away from the solar surface, the resolution is more coarser. I mean, it's more like
So
the cell
that
size
means
is
that
larger.
your reconnection is actually occurring at a length scale of 7 megameters.
Yeah, yeah.
Okay, thanks. I'll think more about it.
Yeah.
Yeah, I think we have a few more questions from Ritesh and Sushri. So any one of you wants to just unmute yourself and ask the question. Ritesh?
Yeah. So Nitin, you mentioned somewhere that there were multiple eruptions and standard flare CME kind of thing. So how do you see those post-eruptive effects, like the rising flare loops and foot point separation kind of? So do you see something similar in your model too? Or like, are you able to resolve those structures?
Yeah, I mean, post CME effect, I mean, in terms of the standard flare reconnection, we do see that. I mean, we were able to see the elongation of the central arcade and the reconnection happening. And also, when we do the magnetic field line, when we plot the magnetic field line over the domain, we also see the formation of the flux rope or the reconnection happening, this standard flare type of reconnection happening after the CME.
And one more thing, like your domain, your simulation domain runs for more than 24 hours, right?
Yeah, I mean, yeah, for the shear is applied for 27 hours, yes.
And what about the reconnection? Does it last that longer?
No, it's not that last. It's just reconnection happen I mean, for lesser time. It's just the CME forms and it propagates. So
Okay.
yeah. So it's the entire time I'm talking about. It's not the reconnection is happening for 27 hours. It just happens for a few moments. Yeah.
Okay. Thank you.
Yeah. So Sushri, you can ask your question.
Hi Nitin, nice talk.
Yeah.
I have a question regarding AMR application. So when do you apply it? And I may miss the point, like where do you apply it from this question? Could you repeat that answer? And so my first question is when,
Yeah.
like,
Yes.
yeah.
Yeah, so actually the AMR we applied because after the applying the shear at the base, the reconnection is happening and the currents are forming in our system. So after when we reach the equilibrium and when we are applying when we are applying the shear at the base, we apply this AMR criteria, and this AMR criteria is entirely based on the formation where the region in the particular region where the currents are forming. So this is there is a certain parameter which above which we give some value, and above which the AMR resolve the domain into further levels, and below which it don't. So this is based on the current forming region, where the currents are forming in the region.
Then in that case, in case of multiple eruptions, then how do
Yeah.
you handle that?
How do you handle mean by that? I mean, so
Like,
it doesn't. It's like we don't. I mean, it's like wherever the currents are forming, it automatically resolves to this to reduce the computational time. Because if we apply the if we do the simulation in entirely higher resolution, so it will take more time. So what we do is we apply the MR in particular region where region of interest, and it could be anything based on where we see the sharp change in density or sharp change in temperature. But for our cases, we are interested in the reconnection region, so that's why we applied it only based on the current scenario.
so you're saying that the AMR applicability is intermittent based on the formation of current sheet in your model. So that is
Yes,
already automatically it's the model is
it
doing
applied.
that.
Yes.
So
I mean, the
there
code
is
does,
something.
not the model. It is the code. Code does.
Yeah.
Wherever it finds
So
the.
there may be some scheme so which is doing it whenever you have some
Yeah, so
criteria
it's
for
in.
that scheme.
Yes. So we have some criteria for that. I studied there is some parameter. There is some parameter.
Okay. And I forgot. So how? So what was your how far you go in your simulation box, like the end
So this is up to 10 solar
how
radii because
10 solar radius. Okay.
yeah, because also the reflection effect. So to avoid that, we have kept the 10 solar radii.
So what boundary conditions you use for the upper one?
So
And
at the upper boundary, all the parameters are continuous.
okay, and the side also they are continuous. I mean,
No. So we have to fix the density, and because we have to fix the density and also the dipole structure. So there are boundary condition as in this R square BR. There's some of the parameters are fixed at the inner boundary.
and for the bottom boundary, could you repeat that?
Yeah, at the bottom boundary because it's like yeah. So these are the boundary conditions.
Okay, this is for okay. Got it. Yeah, thanks.
Okay, so I think we are done with the questions. Nitin, we have one suggestion from Vaibhav.
I'll calculate that. Yeah.
Which is perhaps you but thank you so much. Thank you, everyone. I'll just stop recording.